In astronomy, distance is everything. Anything we want to know about something depends on how far away it is. Without knowing the distance, we won't know if an object we see is the size of a cell or the size of a galaxy. If we want to know how massive something is, we need to know its distance. If we want to know how much energy it produces, how powerful it is, we need to know its distance. And in astronomy, we have the interesting thing is we can tell how old an object is based on its distance because light only travels at 300,000 kilometers per second. And so when we look at a distant object, we can actually be looking back in time. If we know it's distant, we know how far back in time we're looking. But measuring distances in astronomy is not straightforward because we cannot lay a ruler down between us and the nearest stars or galaxies. Rather, we have to rely on how things appear. Now here on Earth, we, in our everyday lives, judge distance by how things appear. In astronomy, we can imagine doing the same thing by looking at, for example, how bright things are or how big they appear. So let's look at how two astronomers who are roughly the same size appear at different distances. So Paul and I have just taken 10 steps away from the camera, and you can see we're about the same size. Now I'm going to take an additional 20 steps, and you can see the further away I go, the smaller I appear. Here I've taken 30 total steps versus Paul's 10, and I'm much smaller. Let's understand what that means. So when we go out and we look at things, we're actually going, if you think about it, and looking around what is really an angle. So when I go out and I look, I'm looking around 360 degrees. And when I see something, I'm seeing something that is some fraction of that circle. It's an angle, which we'll always refer to as theta. Now, let's look at this in detail in terms of the math. So imagine I'm having my eye, and I'm seeing something that is a long ways away. So for example, the light's coming in here at infinity, and it's forming an image on the back of my eye, my retina. So we get, for example, light coming from that direction forms on one part of my eye, and something that's a different distance away will come through and form an image on the other part of my eye. And so the angle here of the distance between these two objects is theta. So the further an object is away, the smaller that angle is going to be, and the smaller it's going to appear here on the back of my eyeball. So if we think about measuring this mathematically, let's go through and give ourselves a circle and see what happens when we start applying our math to it. So when I look at an object here of an angle theta, or some size, we have an arc S of the circle, or a length L. And you can see L and S are not exactly the same. We'll come back to that in a second. So the circumference of a circle, if we think about it, is 2 pi times r, which is the distance from me to the edge of the circle. So that's 2 pi r. And when I'm only seeing theta of something, I'm only seeing a fraction of the circle. So that really is theta over 360 degrees is the fraction of the circle I see. And so that arc of the circle's length S is 2 pi r theta over 360 degrees. If the r becomes very large, so the circle becomes very big, you can imagine that L and S would become very close to the same thing. Because when you look at a circle up close, it ends up looking like a bunch of lines connected together. And so if r is very, very large, then you end up with this relationship that the length L is equal to S is equal to 2 pi r theta over 360. Now, in math, we often use angles not in degrees. We use them in radians. And so a radian, remember there's 2 pi radians, is equal to 360 degrees. Or 1 radian is equal to 360 divided by 2 pi degrees. So I can rewrite my equation, which is that L is equal to r theta, because the 2 pi over 360 cancels out, if theta is in radians. So if I measure angles where the distances are very large, which is always the case in astronomy, I can use this relationship, which is that the length of an object is equal to its distance times its angular size, or in other words, theta is equal to the length divided by the distance r. In other words, things become smaller proportionately to the distance that they appear. Now let's see how that works in Paul's and my experiment out at Mount Stromlo. So we expect in our experiment that the angular size of something is inversely proportional to its distance. In this picture, I've taken 30 steps to Paul's 10. So my angle should be 3 times smaller than Paul's. We also know that when we look at something, that angle translates to pixels, for example, on our camera detector, or the size on the detector. So if we measure how many pixels Paul is, we see he's 506 pixels across, where I'm a mere 167 pixels. The ratio of 506 to 167 is 3.03. So not exactly the 3 to 1 we expect, but of course our steps and our sizes weren't exactly the same either. So what we expect has been seen in our experiment.